All right, and welcome everybody to a special presentation here. We're going to be talking about emission spectra and blackbody radiation. So while our channel spends a lot of time talking about heliophysics, space weather, even Earth weather, we decided that it would be prudent for many of our viewers, right, to just spend a moment talking about emission spectra. So we'll be talking about the electromagnetic spectrum. We're kind of, I think it's safe to say that we're going to keep things in the realm of photons here. And so as far as things like the solar wind, the protons that are in the solar wind stream, that's not what we're talking about. We're talking photons for this whole video. And welcome to Eugene, our special guest, who's been on many videos. What's good, Eugene?
Hello, everyone. Well, if you look at my next video, which I'm currently rendering, not much is good around here in Belarus. But
What's your latest?
Than that,
what's your latest about?
it's the part 2 of White Wings of Liberty. So it's been a year since our elections, and now I'm making like a follow-up.
That was a good one.
Super depressing.
Yeah,
it was
it's
like the hardest video to record, like emotionally, like. And it's very long.
A little bit of open air gulag sort of thing going on, or?
Yes, I'm actually mentioning you because of your jokes about gulag, like near the end of the video.
Oh, geez. Well, I'm sure I'll be in one soon, as if I'm not already.
Anyway. Yeah, things are not as bright as we hoped in the world currently. So yeah,
I would tend to agree.
But in my country, it's even worse than average.
All right, so let's just take a moment here, and so we're just looking at the sun here, and you know this is a very specific emission spectra. So just to sort of preface the video here, what we're looking at here is a very specific portion of the electromagnetic spectrum in the UV range, 304 angstroms, which coincides with ionized helium. And you know this is one of the more popular sort of wavelengths. A lot of people, when they think of the sun, they think of these SDO chromosphere UV emissions.
And one thing you have to remember is that the color is arbitrary. Like it just records the brightness, so it's not really red.
Exactly.
Right? It's sort of white, actually.
Yeah, so this is a higher frequency.
Color it red to distinguish from other colorings we have for SDO.
Right, and that's why different spacecraft tend to sort of color this wavelength the same way. So you may look at such as GOES 16 imagery, I believe, or also SOHO imagery. They just to make it a little easier, because there's a lot of information that you're looking at there. So let's just bring up an image of the electromagnetic spectrum. I'll pause. All right, so here's an image of the electromagnetic spectrum, and let's see here. The portion that we're talking about is just to this side of visible light, in between visible light and X-rays, the UV spectrum, right?
Yeah.
So that's what we're talking about when we're looking at those SDO images. And
yeah, it's to the left side of it,
and
UVC.
And sometimes you'll see these charts in the opposite direction. This one is like larger waves to the right, I guess you could say that way. Often you'll see these going the other way. Just realize that gamma rays are to the left and radio is to the right.
Yes.
And so when we're looking at things like astronomy and cosmology, one of the things that we use to look at really distant objects are emission and absorption spectra. And just to give you some idea of how light works, I guess, when we're looking at stuff in the visible portion of the spectrum, it's because those objects are reflecting the waveband, the wavelength that we're seeing, and it's absorbing the rest of the wavelengths, which is the important part. That's really the physics behind how light works. Right, Eugene?
Not necessarily. Some objects do emit their own light, like, again, I don't know, your light bulb or whatever, or a fire, like,
Sure. And well, yeah, okay. So if you're talking about a light that isn't an object that isn't illuminated, so we're not in the realm of stars here. We're talking about like crayon wax, right?
Not sure what it is, but probably.
Well, so the point is, if you color with a pink crayon, that wax is absorbing the frequencies that aren't pink. That's why
Yes,
why it looks
yes,
pink.
yes.
So that's
So
really
it's actually absorbing something around green, like the middle of the spectrum. Because if you combine blue and red, you get sort of like purple slash pink, right? So
right.
it's probably absorbing most of the middle of the spectrum.
And so, Eugene, can you like go just briefly into how a photon, the different mechanisms by which a photon is created? I'm not sure. Where do you think we should go next on our trip toward explaining blackbody radiation?
So a photon is usually thought to be produced by electron, like changing its energy state, if that makes sense.
Yep.
Like in atoms, according to quantum mechanics, electrons can have different energy states, like different energy levels, etc. And so when electron jumps from one energy level to another, for some reason, or even just spontaneously, it would either emit or absorb a photon. So if you like shoot photons to a piece of matter, then the electrons may absorb these photons and jump higher in their energy levels, let's say. Or they can jump out of the atom completely if you have enough energy in your photon. That's what is called a photoelectric effect. So, but if an electron has energy of its own, again, for some reason, maybe like thermal collisions or whatever, it can jump down in its atom and then it would emit a photon. So this is pretty much the mechanism. But that's when we're talking about the single atoms, but we can have like more complex structures, like in crystal lattices, let's say, where electrons have much more possible energy states. Like in metals, electrons are almost like free, etc., etc. So it gets a little bit more complex than that.
And it sort of has
Uh,
to do with the crystalline structure of those metals and how electrons are able to sort of move around through and around the crystalline structures.
yeah, I mean, theoretically, even protons or like nuclei can emit or absorb photons, but the probability is, as far as I know, much smaller than that for the electrons. So
So
we're
let's just
mostly dealing with electrons.
yeah, let's just bring up an animation here. All right, so here we've brought up this this GIF animation, and it's, by the way, folks, it's pretty hard to find a GIF animation of an electron producing a photon for some
Yeah,
reason.
we've just spent like 10 minutes on pause in this video trying to find anything decent, and we didn't. So,
We're both kind of getting mad here, but what this is attempting to depict is some kind of a nucleus with an electron getting close enough to its electron shell region to get stuck in the shell and then go through this rapid like deceleration and emit a photon.
yeah,
It's
so
Bremsstrahlung, right?
Not exactly, but it's close to that. So what we see here is what is technically called recombination. It's the inverse process with respect to ionization. So ionization is when you take the electron out of atom, and recombination is when you add the electron to the ion, so that you would have a neutral atom, or at least less ionized atom than previously, right? So
Right. Trying to
we
reach
have
static equilibrium.
like a free nucleus and a free electron, and then they combine, and the photon is emitted because free electron had some extra energy, and when it's bound, it loses this energy, so it has to spend it somewhere, and that's where the photon comes in.
And
And
that's
there's also another photon coming towards the nucleus, and this is just kind of illustrating the fact that the electromagnetic interaction, according to modern quantum field theory, is carried by the photons. So, yeah, pretty much.
all right. So that's one of the way photons are created there. I just put that purple arrow to show our viewers the photon as it is not labeled on the image. Oh, it is. Okay, it says two photon. Okay, fine. Yeah, so that red wave there, that's a photon. And what's up with the emission spectra of that photon, Eugene?
It would be a single line, like a definite frequency. So it wouldn't be. It would be actually. It may be. Wait, I'm kind of actually struggling with this myself right now
Well, the
because
frequency depends on its initial energy state when it gets before it gets stuck
yeah,
in it.
yeah, sure. Like how much energy the electron have, how much it needs to spend to, remain bound. So yeah, but yeah, it would be, since it's a single photon, it would be just, a single frequency, like very sharp line.
All right. And let's bring up another graphic here. All right, so what I've brought up here is the CDS portal, which shows us a bunch of different emission spectra. And this is the 2-mass scope. You can look this up yourself. This is a Vela pulsar. Our channel regularly, Eugene, you may not be aware of this, we regularly talk about the Neil Gehrels Swift Bat X-ray Observatory. Neil Gehrels was very interested in the biggest explosions in space. And so this X-ray observatory is named after him. It's got over 1,000 entries. One of them is the Vela pulsar, which is located way off to the right side of the Milky Way galaxy. We'll just call it the right side for the sake of this video. But it's off in the outskirts. So we're looking at an infrared spectra here, and you can see down here in your lower left, perhaps, the Milky Way galaxy. The galactic core is someplace toward where my pointer is. I think it might even be off screen from this view. So if you zoom way in here, you'll find the Vela pulsar in infrared is not very bright. There's not really a lot to see there. However, if we look at the other end of the spectrum, maybe not gamma rays, but looking at X-rays, indeed you can see that it's quite bright at that same zoom. So there's the Vela pulsar in false color X-ray. And so this is a very energetic pulsar, to say the least. And it's very, very different in ultraviolet as well. So there's the ultraviolet photons from around that area, and it's like you can't even see a feature there in that wavelength. We'll go back to X-ray. Eugene, comments?
Can you also put on gamma rays? Is it bright in gammas? I would imagine it
I
is.
believe there is a bright spot there in gamma. It usually won't be. It
It's
usually
right
won't be
on top of-
centered right on. Oh yeah, very, very bright in gamma.
Yeah, just as I expected. Well, pretty much like usually X-rays are produced. They can be produced by nuclei themselves. Like again, according to quantum mechanics, nuclei have energy levels just like electrons do. So, a proton can transition from one energy level inside the nucleus to another, and therefore, like if it was excited for some reason. Again, could be multiple reasons for that. It can like fall down, in air quotes, in its energy, and it would emit something. And since, like, generally speaking, nucleus's energy levels are like orders of magnitude larger than atomic energy levels, therefore the photon that would be emitted would be most likely in X-ray range. So,
All right.
yeah. So, but that's only one mechanism. Like nuclei can emit X-rays, but another mechanism is if you have just free charged particles, like let's say it could be protons, it could be any other type of ion, it could be electrons. If they are accelerated by electric fields or changing magnetic fields, let's say, they can also emit like higher energy photons such as X-ray or gamma rays. So, and I believe like probably in astrophysical realm, this is more important. This is more frequent mechanism of emission of gamma rays and X-rays, like accelerating charged particles, basically. Because again, according to basic electrodynamics, any acceleration of charged particle would produce EM radiation, and a particular case of which is X-ray or gamma ray. So
Right. And so how much does this tell us about the underlying structure that's producing the gamma and X-rays?
I would say not much, to be honest. I mean, we just see like a bright spot. That's pretty much it.
I hear you.
Yeah.
And on that note, we'll go back to gamma ray because it is, as you can see, I believe this is actually the brightest gamma ray source because
I don't know.
I mean,
not sure.
Look at the rest of the Milky Way galaxy.
Oh,
this one is,
yeah, it's really bright.
Yeah. I
Okay.
was not aware Vela
It's
was that bright in gamma myself. Actually, I may not have ever looked at it in this before, but
it's
it's
probably pretty close to us. I mean,
yeah.
since it's so bright.
I don't know. I think it's. I'm not sure, but the point is, I think it probably has a jet oriented at us because of the way it looks in
Yeah,
the way
fair
it looks
enough.
in X-ray. You get a little bit more of a feature there for some reason.
Hmm.
Gamma ray surveys take a long time, I think. So
Yeah, because it's really hard to detect gamma rays because they penetrate everything so easily, so you can't catch them that easily.
I'm not
You
sure
know
if
what I
that's what
mean?
she
Like,
said, but it was close. Yeah, exactly.
okay, fair enough. By the way, like speaking about that, do you know that the wavelength of the cold hydrogen, like atomic hydrogen, it's 21 centimeters, which is I don't know how much inches, but it's it's the golden standard of the universe. So
Ah,
um,
so
I'm,
it's
I,
equivalent to
I
a
myself am
certain
not
length
quite
of.
qualified for that, if you know what I mean.
Yeah, I don't know. I'm
Like,
definitely not an expert in this field, nor do I plan on becoming one. But thanks for.
but again, it's like the golden ratio. The universe itself tells us that this is important. This length is like what you should strive for, if you know what I mean.
So anyway, folks,
Whatever. Let's
I just
let's
want to zoom.
just yeah.
I'm going to zoom back out here again, and I'm going to switch back to the 2 mass because if you look at the core of the galaxy, a more busy spot of the Milky Way. So here now we're around the core region, somewhere around there. It's fairly symmetrical. And if you zoom way in here in infrared, it's very hot. There's a lot of dust and gas there. And, in infrared, it's very hard to see things. But once again, when you break this into a different emission spectra, right? X-ray frequencies are going to show you a lot more obvious features. These are probably some giant blue stars that are like near to the galactic core. There's all kinds of stars orbiting the Sagittarius A star at relativistic speeds and so on. And then of course, if you look at UV, you're going to see a little bit more of a plasma structure, I would imagine. And you can see this survey is a little bit spotty actually. That's the Galix, by the way. It does still
Well, I
offer.
mean, if you have a very good resolution, like very narrow camera, then obviously it takes time to, survey everything.
Yeah, and I'll try to find a good UV source here. I see some bright areas. There's
You
an
can
nice.
also see distortions from the projection of, like a spherical thing onto the plane, like the flat image.
I'll take your word on it.
Like if you zoom out, you can see some distortions.
I
I
mean,
mean, like try to look at where two circles are near each other, like two circles combined. You can see it's kind of,
looks like
kind of
some artifacts in there maybe.
pancaked a little bit to one
Yeah,
side.
and a busy spot in space like that, you're going to expect more of that. If you go to an emptier spot in space, you're going to see less artifacts. If the survey is indeed complete in that area, it looks like this one isn't. Oh, okay.
Yeah, they probably didn't care enough to watch the
Yeah.
video. They actually did.
But anyway, this is something that comes into cosmology all the time. We're looking at different objects and trying to figure out how it is they do what they do, right? So let's bring up another graphic here. All right, so now just to talk about blackbody radiation, we talked about different structures in the universe, and one of the ways we see structure in the universe is by looking at these specific emission spectra, and oftentimes it does tell us stuff about what's emitting it. For example, when we look at these specific emission spectra on the sun, we're seeing chemical reactions largely with iron going on. Most of the wavelengths from the SDO are iron, like 171, 131, 94, 211, 193. Those are all iron emission spectra. Which brings me back to blackbody radiation, because, well, it seems sort of overlooked when it comes to heliophysics. What say you, Eugene?
Not sure I agree with overlooked, because this is exactly what all the textbooks say, that the sun emits as a black body at roughly 5.5 k or roughly 6,000 k.
Yeah,
So
something like that. At least the hydrogen alpha portion is definitely around that wavelength. But what? Let me just rephrase. So when we're looking at the SDO, 304 angstroms, it's just above the visible spectrum, right around here. Higher frequency than, blue light, violet light, ultraviolet light.
yeah.
But the total emission from the sun is more like this, like a black body spectrum, which means,
I also believe that this graph is somewhat wrong. Like violet, like actual violet, which is like lower wavelength than blue, looks different. Like it's purple here, whereas it's not purple in reality. Like it's sort of very deep, very dark blue, like navy type of blue.
well, it just has a 700K thrown in there. It's not like it's trying to represent it in a specific spot
No,
or
no. I
anything.
mean, the color that they use for this part of the spectrum, the left one, I think it's wrong. It's purple, but it's not purple in reality, because purple is a mixture of blue and red. It's not actually in the spectrum,
It
which is
just,
actually, I mean,
okay.
we can talk about this as being like the royal color and the color that is never used in flags because it's very hard to produce and blah blah blah. But it's not that. It's the wrong color. But I digress.
Well, anyway,
Never
let's
mind.
so let's talk about sort of we have to talk about, the sun's emission of black body radiation versus the emission of specific emission spectra, right? So the sun is bright in various different lines. Obviously the brightest in hydrogen, right? But it also emits a
Uh,
black body
mhm,
spectra. And perhaps this is
yes.
giving us insight into things like why sunspots are dark, right?
I'm not sure about this. I mean, yeah, there is a thing called Fraunhofer lines, and these are lines of absorption. Like, you can actually find it in web search, not Google, just web search.
Yeah, please
Fraunhofer.
don't use Google as a verb. I'll put that on the
So,
screen. So we've brought up an image here of Fraunhofer lines. Eugene, what do you want to say about this?
yeah, so the sun emits pretty much black body spectrum, not quite, but very close to it, right? So it's one thing about black body spectrum is that it's how do you say it? Continuous, right? So it's like a continuous curve of emission power versus frequency, let's say, or wavelength. It doesn't really matter in this context. And on top of that, some of the elements, some of the atoms slash ions in the sun's atmosphere uh, absorb certain frequencies, like you can see here. So this is basically what this picture is showing us, is a continuous spectrum that we see from the sun, which contains obviously all the possible colors we can see, because again our eyes are evolved to do that because we live near the sun, right? But there are certain like gaps caused by exactly that, like the certain elements in the atmosphere of the sun absorbing these specific frequencies.
So that's
So this is what
absorption.
is called,
So that
yes,
so there
this is absorption spectrum.
excellent. And thanks for explaining that. So that's the Fraunhofer lines, the portions of the spectrum which are phantomly absent.
Yeah, you wouldn't notice that because they are very narrow. I mean, with like if you, let's say, dissolve the solar light through a prism, like Newton did, promoting LGBT again, as we discussed off screen, whatever. So you wouldn't notice that because they are very narrow. So it still looks like a very, very like kind of how do you call it? What's the right word? I'm sorry.
That's okay. Avoid. Avoid in the spectra.
Smooth, that's the word I was looking for.
Okay.
Smooth spectrum. you wouldn't see those gaps because they're very narrow. But
Right, right.
with a good resolution, you can see them.
And that brings me to my next question, Eugene. What do these gaps tell us about the material in the sun's atmosphere?
Well, if we know what kind of ions can, let's say, produce, in air quotes, this absorption, then we can tell the elemental composition. And this is exactly what spectroscopy does, like I don't know if that's a right word, like heliospectroscopy.
Yeah.
By the way, that was, I believe, one of the ways how helium was discovered in the first place. Because, like, why is it called helium? Is because Helios, the god of sun in Greek mythology. So it was first discovered in the spectrum of the sun. Later, it was found in natural gas on Earth, which is the main actually source of helium.
And so anyway, the point is, looking at emission and absorption spectra give us insight into the material emitting the spectra or absorbing the spectra, in this case of the Fraunhofer lines. And so when we're looking at complex molecular clouds and stuff at great distances, we can often use these two techniques together to get pretty complicated information about what is in those complex molecular clouds, which I guess that brings me to Robitaille. So let me bring up another graphic here. Go ahead, Eugene.
Yeah, let me just give a brief comment, like an expansion, I guess, add on, so to speak, to this. So when we're talking about, let's say, a lot of particles together, not just like isolated ions or electrons on their own, there are phenomena of so-called broadening of spectral lines. So here you can see like very sharp lines, and they are actually exaggeratedly thick, I would say. In reality, they are much sharper. But in reality, when you face like an atmosphere or even condensed matter, even more so, there are phenomena of broadening. In particular, the gas under pressure, like the more pressure there is, for example, the more like thick lines it would emit or absorb because of various phenomena. I mean, regarding the pressure itself, because what is pressure? It's fundamentally electromagnetic interaction between molecules, right, or atoms or whatever. There is also Doppler line broadening, which is when basically the molecules move with respect to each other, and that the faster they move, the thicker the line gets. So when we're talking about not like a single photon from a single electron, but like a big chunk of matter emitting photons, then we often get this broadening. So that's one actually method of measuring, let's say, temperature, is to see how thick the line of absorption or emission is, or pressure, by the way. But it's just a caveat I want to make here. So, okay.
All right, that's fine. And let's move on to Robitaille, who is officially my favorite spectroscoper. I'll bring up a graphic on Robitaille. So let me bring up Dr. Robitaille, Pierre-Marie Robitaille's YouTube page known as Sky Scholar. I would invite all of our viewers to check it out.
You should correct yourself.
Yes, I believe, and Eugene corrected me here, I believe it is known as a spectroscopist. And if you're wondering Robitaille's academic credentials, they're ridiculous. He has 2 PhDs, and he currently holds the world record for nuclear MRI imaging resolution. His colleague said, "You'll die if you put your head in a 8 Gauss magnetic field," and Robitaille said, "Hold my beer."
It's not 8 Gauss, it's 8 Tesla.
Oh,
Gauss is
sorry. Thank you, Eugene.
Times weaker than Tesla.
Thank you, Eugene. So, and this is one of my favorite videos. That's why you can see it's been played multiple times here. It's only got 15,000 views. The history of the gaseous sun. So, part of the just to give you a little background here as to why this exists, is because part of the part of the basis for all of cosmology is heliophysics, and our beliefs in what's going on in the core of distant galaxies is all based on the standard concordance model of stellar evolution, which is really some 1860s thinking. What say you, Eugene?
Well, not quite as old, but like really it started with Eddington solar model, which is roughly like 1920s, maybe. Eddington was, by the way, one of the guys who, in air quotes, confirmed the general relativity with his observation of gravitational, in air quotes, lensing near the sun, right? So he's a pretty famous guy. So yeah, I would say that that was roughly the start of the solar model. I mean, the again, in air quotes, mainstream solar model. And then again, he had opponents like James Jeans, for example, the British scientist, who maybe Eddington was also British, I don't know. Anyway, so Jeans was holding a point that the sun is actually liquid, so he was much closer to Robitaille in this sense, or rather Robitaille is closer to him considering the time difference. So yeah, and like this was in particular one of the points of Jeans's thinking is that why do we observe so many binary stars? Like probably most of the stars in the universe are binary, right? So is that it's because the stars are liquid, and as this piece of liquid, roughly speaking, rotates, it can split into two. So that's what his idea fundamentally.
I understand the reasoning. Just a very basic sort of a feature of a rotating object under stress in space, perhaps made of condensed matter. I might add.
Yeah. By the way, I'm not sure if I'm correct on this, but I have a feeling that you don't understand the term condensed matter. Like in physics, what we call condensed matter is basically liquids and solids and everything like that.
Right.
So it's not some special type of matter. It's like not a gas or plasma, basically. That's what condensed matter is.
Right. Liquid water in a glass or the ocean would be condensed matter, but water vapor would not be condensed matter.
But vapor is not. Yes.
I don't know what you think. I don't understand about that. But cheers. Thanks for clarifying. So anyway,
we once we had a video where we talked about like high pressures, like diamond anvils and stuff, and I've had an impression that you think condensed matter is something like special, something other than solid and liquid. So yeah.
Well, superionized matter.
Be my bad. I might be misinterpreting you. So.
I was probably talking about condensed matter under millions of atmospheres of pressure, at which point it tends to behave like a metal. Which kind of
it would be certainly a condensed matter under these conditions, yeah. So yeah.
Well, assuming that they're not super hot, because the phase diagram of hydrogen is what's coming into play here, and ultimately we don't know what happens at the ultra high pressure end of the phase diagram of hydrogen. It could turn into a solid. That's the theory. That
we actually do have some idea. I mean, there were experiments where people acquired metallic hydrogen, but yeah, the only problem is it's very short-lived. Like all these experiments are really transient, if you know what I mean. Like they really need to get really high pressures and really high temperatures. Maybe.
Okay, let me just cut in there and bring up another graphic. Yeah, so okay, we're back, and this is so here's a phase diagram of hydrogen just to give you an idea what we're talking about here. There's a point. I don't believe that we've made this in a lab. We've certainly made this in a lab.
I think we actually did. I'm not sure. I don't have like any links to confirm.
Well, we may have
ready.
In any case,
I think we did.
It's fairly certain that this superionized state of hydrogen at this high pressure, which I believe is something like 1 million atmospheres, it does behave like a metal. It turns black.
If it's pascals, what is log? Is that 10? Base
Pascal.
10? I don't know. I know what Pascal is. I don't know what log means. Is that base 10 or base 2 or I don't know. Whatever.
I think
if it's base 10, it means like 11 means 10 to the
times.
power of 11, right?
Yeah.
So it would be like hundreds of gigapascals, and our atmosphere is 100 of kilopascals. So
okay, we have to tie.
Be,
we have to tie this back into the sun here. Let's get back on track. So Eugene, I've put up Sky Scholar's page here, Pierre Marie's YouTube channel. Tell us about what do you know about blackbody radiation? I'm dying to hear about it, and so are our viewers.
Yeah, so one of the points that Robitaille makes is that the blackbody radiation, like a frequency / energy curve, is derived from Kirchhoff's law. That is Kirchhoff, the German guy.
Right.
But by the way, in German it means church yard.
Correct. And Kirchhoff's law is associated with blackbody radiation and a perfect absorber.
So Robitaille tries to demolish Kirchhoff's law, and therefore he thinks he would demolish blackbody radiation curve. But the problem is that modern derivations of Planck's curve and therefore like blackbody radiation spectrum do not imply Kirchhoff's law. They actually imply electromagnetic field and like Boltzmann's statistics, and like you just well, it would be kind of hard to explain, I guess. But so in modern derivation, I'm trying my best, so hold on to it. So in modern derivation, we need an electromagnetic field that is, let's say, a bunch of oscillators, i.e. like vibrating thingies.
Like a vibrational planar lattice structure?
Sort of, but it's a field. It's what this field is all about. Like the electromagnetic field is a bunch of oscillating thingies.
Sure, right. The emitter of the photons, the electromagnetic radiation.
Yes. They're called photons.
So we're back to photons. Excellent. Thank you for bringing us back.
Yes. But for blackbody radiation curve, i.e. Planck's curve, to appear, you need an electromagnetic field to be able to produce and absorb. So like any number of photons can be both produced and absorbed at any frequency, right? So, and if you like pump some value of energy into this system, where again, any number of photons at any frequencies can be produced and absorbed, you'll get a blackbody curve. That's what the modern quantum field theory states. So you just need to pump some energy into electromagnetic field itself, and if it has the capacity of producing any wavelength and absorbing any wavelength of photons, it would do so and it would produce this curve. So Robitaille's point is still sort of viable, even in this perspective, even though his original criticism is not, I would claim, because it rests on criticizing Kirchhoff, whereas the modern science kind of disregards that. So Robitaille's initial point is that only a crystal lattice can do that, what I've just described, can produce photons and absorb photons of any wavelength in any number, right? So he claims that there is one special type of physical system, i.e. a crystallic crystal lattice, which can do that. And therefore, like purely theoretical stance that I just said from quantum field theory, that you only need a system that can produce and absorb photons of any wavelengths in any number, producing, blackbody radiation. So Robitaille claims that there is only one possibility of such a system to exist, and that is a crystal lattice. And it's a valid point, I believe. So in some sense, Robitaille's model of liquid metallic hydrogen sun still stands, because we have not seen, and it has not ever been experimentally proven, that any other type of system other than, solid body, basically. I mean, by solid, I mean crystallic. Whether we have liquid crystals, I mean, we do have them, but whether they can actually be black bodies is a different question. So it's a little bit hypothetical in this sense, what he says about liquid metallic hydrogen.
And one thing we can say for sure about gaseous plasma is that it will not emit radiation via a black body spectrum.
Wait, I'll return to that.
Excellent.
A little bit later. So whether liquids can do that, it's under question currently. So whether liquids can form like semi sort of like crystals, which can induce all kinds of oscillations to produce, all kinds of photons to produce black body spectrum. It's under question, but I think that the theory still stands. Like, well, I would actually call it a hypothesis, but it's my own taste. But you can call it
That's
a theory. I mean, it's pretty solid, no pun intended. But modern heliophysics has its own answer to that. So its own idea of how, let's say, the sun can produce black body spectrum. Again, remember what I've said previously, is that in order to have a black body spectrum, we need to have a system that can produce and absorb photons of any wavelength in any quantity, right? So that's a prerequisite for a black body spectrum. So current heliophysics claims that it's actually the electrons themselves, like free electrons, or negatively charged hydrogen ions. There is such a thing. So it's basically a proton with 2 electrons around it. It's not stable, so it disintegrates really quickly, but it exists on the sun. We know it for sure. So it's either free electrons or this H- ions, i.e. proton with 2 electrons, that are producing the spectrum. So free electron can produce anything you want, theoretically, because it's free. Like, it can emit anything, it can absorb anything. So theoretically, it is an example of this system that I've just said, that I just talked about, that can absorb any photons and produce any photons in any quantity required. And just give it some energy and it would emit it immediately.
And so this is the alternative to Robitaille's hypothesis about the way the black body spectrum is created, that it's created by electrons alone and not by a vibrational lattice structure. And because to bring it back where we were earlier in the video, we talked about the way the frequency coming out of the electron losing an energy state or gaining an energy state is all based on the amount of initial energy that it had.
Sort of. So to conclude this point, segment, I guess, the both theories, both like mainstream in air quotes heliophysics and Robitaille's theory, they both agree. They at least they don't contradict the basic quantum field theory statement that in order to produce a black body radiation, you need to have a system which is capable of producing or deleting photons of any frequencies, right? But Robitaille's claim is that the only system that is capable of doing that is a crystal lattice, and the mainstream, in air quotes, claim is that free electrons or negative hydrogen ions are doing that. So this is the main difference.
And I think this brings up another important point, and correct me if I'm wrong, there is an issue regarding where all the sun's electrons come from. And that is another thing that I believe is being explained by the Robitaille theory, in that they're coming out of the intrinsic properties of the liquid metallic hydrogen that perhaps makes up the photosphere.
I don't quite understand what you're getting at, but
this is I don't know. This is pretty in-depth heliophysics stuff, and one of the attempts by all of the hypotheses to explain how the sun does what it does is that there is a flow of electrons coming out of it. There needs to be a supply of electrons in order for the chemical reactions we see happening on the surface of the sun to be happening.
I haven't seen any evidence of that, so I cannot confirm it.
Well, I'll I'll provide some information about that at a later time. Now, in the meantime, and I'll try to put a link in the description to that or in the comments. Now, just to bring us back to the sun here again, and of course we've been pretty much talking about the sun here the whole time, but have you heard something about brightening limbs?
Well, my limbs are sometimes brightened.
No, I mean the sun. I'm not talking about if you're like standing in a searchlight or something because you're trying to escape a gulag. I mean the limbs of the sun.
I'm pretty close to Chernobyl, so that's probably the reason.
Well, we hope you're upwind. That's the main thing. We hope you're upwind and you're not eating any vegetation from there. You don't have a garden planted at Chernobyl, do you?
There were actually quite major fires, like forest fires in Chernobyl area, and people were freaking out in my country. But the official propaganda just kept silent, like nothing, just keep calm. And actually, like myself, I have a video about nuclear energy, and this is way overblown. Like nuclear energy is pretty much safe, like except for when you're actually going into the reactor itself to clean it up, then certainly you would have a what is called how's it called actually?
A bad day? A radiation suit on made out of lead? Deadly amounts of radiation exposure? Yeah, I'm aware of that.
Which you would die, most likely. Whatever.
So Eugene, we're looking at the sun here from the GOES 16 SUVI imagery. And why is it, Eugene, that it's so bright around the limbs? Now, this is UV, not X-ray, so we're looking at 94 angstroms, similar to the green 94 angstroms imagery from the SDO, and indeed the same wavelength, but from a different spacecraft, the GOES 16. And you can see in this portion of the UV spectrum, it's very bright around the limb compared to most of the Earth-facing portion of the disk.
On SDO, it's 131. Actually, so a little bit longer.
Well, the 131 is like an aqua color. The 94 is similar, like an emerald green.
Similar. Yeah, a little bit bluer than this one. Yeah, but whatever. So, in Robitaille's theory, I think he mentions this as one of the lines of evidence in air quotes in his 40 lines of evidence for the condensed matter sun paper, which I actually recommend everyone to read because it's very fascinating. So anyways.
I believe it's called The Sun on Trial, 40 Lines of Evidence Supporting Liquid Metallic Hydrogen as a Solar Building Block. It's a pretty long title, but it's a pretty complicated thing. And it's got
a pretty long paper.
Yeah, it's got 40 proofs and something like 400 references in it.
Probably.
Yeah, it's serious.
Anyway, so in his thinking, like the limb brightening is caused by exactly that, like crystallic lattice present in the photosphere. So what it means is that crystals, as a general thing, and it's, easily confirmable, they emit anisotropically, which means they emit differently depending on the angle you observe them. So they could emit, for example, very low if you look at them like face on, like perpendicular to the crystal lattice, or vice versa. They could emit a lot perpendicular to the crystal lattice. It all depends on the crystal structure in the first place. So,
right, and let me go out on a limb for a quick moment here, since I'm not the particle physicist, Eugene is. I believe this explains why sunspots are dark, in that you're looking at a very flat structure on the photosphere. It's under great pressure. And it's fairly plausible to me that that is liquid metallic hydrogen. That explains the Earth-facing quiet effect, because when you're looking at a sunspot, the reason it is dark because it is emitting at an angle the way a metal would emit from a very flat surface. Meaning if you heat it up to the point where it's going to emit that way, if you're looking at a flat surface, that lattice structure is going to cause the emissions to come out at an angle instead of perpendicular to the structure's surface. So perhaps that's an explanation of both limb brightening and the Earth-facing quiet effect, as well as why sunspots are dark, in my opinion.
It's kind of refuted by observation of sunspots at the limb, because they are still dark, even though you observe them at a huge angle. So I would disagree with that. But anyways.
Well, that's true, but the X-rays, the sun is bright around the limb in X-rays at all times.
Yes, I would completely agree.
And when we see a flare, the flare is coming out of, correct me if I'm wrong, it's coming out of the very lower chromosphere, like the the lowest portion of the corona at the highest, more like inside of the
Yeah,
chromosphere.
it's not even corona in most cases.
But it's definitely not like when we see a flare, like a big flare, we don't see that at the photosphere level, right? We're looking at that in the chromosphere.
Yes, absolutely. I would agree. It's never at the photosphere.
And so what we're talking about here, folks, if you don't understand the layers of the sun, this portion out here, that's the corona, and this 94 angstroms portion, that's all chromosphere.
I would actually claim you took a little bit of chromosphere into your corona picture.
Yeah, I was trying to stay right on the edge. It's literally the edge of the disk, the part that looks like a surface. That's where the chromosphere ends in this imagery.
Actually, like the thing you see the brightest in this picture is the chromosphere, like at the edges.
Yeah, I guess so.
It's
but anyway, if you see a prominence,
maybe like 100,000 kilometers above the sun, something like that.
I don't know distances, but
I'm not that specialist in the solar physics. But
I try not to memorize. I try not to memorize things like that, as it doesn't really.
When we're talking about corona, it's like things comparable to solar radius. So maybe like 2 solar radii from the surface. That's the corona.
Anyway, the point is the corona is the sun's atmosphere. The chromosphere is the part that we're looking at all these 3-dimensional looking plasma features on all of these different wavelengths from the SDO and the GO 16. And the photosphere is the area underneath the chromosphere, which is what you're seeing when you see a sunspot. Correct me if I'm wrong, Eugene.
Photosphere is usually defined as the visible, in air quotes, visible surface of the sun. So it's whatever you see as the surface of the sun. And so mainstream, in air quotes, heliophysics usually says it's like an illusion, right? That the sun doesn't really have a surface.
It's maintaining that, quote, surface as a result of a combination of gravity and gas pressure from the internal nuclear fusion dynamo. That's sort of the...
Kind of, probably something like that. But
there's an external force emitted by the alleged nuclear dynamo inside the sun, which is at equilibrium with gravity and helium production and so on. That's sort of the standard concordance, the standard concordance stellar evolution.
Robitaille claims that the solar photosphere is the actual physical surface. So it's the actual liquid, which is we are observing here. And one interesting thing that I've actually mentioned in one of my previous interviews with you, I mean your interviews with me, I guess, is that Robitaille actually thinks that the real, probably in air quotes again, temperature of the solar surface is much, much higher. It may be like millions of degrees, but what we observe as 6,000 K roughly is the apparent radiative temperature, right? But since liquids don't actually like to emit that much because their main means of energy transition are convection and conduction, thermal conduction, I mean, not like electric conduction, but thermal. So the emittive radiative temperature that we observe from the sun does not actually qualify as the real, probably in air quotes, temperature of the sun. So Robitaille says that the sun is actually millions of Kelvin hot. It's just not emitting as much as it would otherwise because it's liquid. So that is his statement, and it's absolutely contrarian to any mainstream, in air quotes, statements.
Yeah, and there's a lot that goes into this, because in order to measure the temperature of something, it's not as easy as sticking a thermometer in it. You're trying to measure something that's 93 million miles away here. Is it at static equilibrium, thermal equilibrium? What is the pressure? And so this is a lot of the stuff that Robitaille runs into, and his videos show great stuff about the believed pressure as you go through different layers of the sun and stuff like that. Definitely check out the Sky Scholar channel. It is, I believe it's going to cause the rewriting of cosmology. Anything else to close out the video, Eugene?
I don't know. We could have talked about CMB, but I believe it would be an overkill.
Let's just do another video soon about the cosmic microwave background. Exactly. We'll just do another hour-long video about the cosmic microwave background because it's pretty complicated. Stars and galaxies are emitting a lot of radiation and a lot of particles as well. So
if I stay out of Gulag,
well, we'll do our best to keep you out, although being on our channel is probably not helping things out. Anything else you'd like to add, Eugene? We've taken the solar imagery off the screen to close things out. Thanks for tuning in, viewers.
Yeah, I would like to thank everyone who is interested, and like if anyone has any questions, wants to discuss anything, like contact me. I'm very glad when somebody actually takes interest in whatever I'm talking about. So we can talk about anything you want. So yeah.
And make sure you subscribe to Eugene the Philostopher.
The Philippines, it was probably like a trans people. No.
Oh, look, it brings up it brings up a specific
It's actually my most popular video, which kind of is bad. Like I don't like that, but yeah.
Oh well. So anyway, everybody subscribe.